So we have seen that while processing n number of instructions, if we are using pipelined approach compared to non-pipelined approach, we definitely have a performance improvement. But how to measure this performance which can be achieved by pipelining, or what are the parameters of measuring the performance? We know that in pipelining, once the pipe is filled, we will get one instruction out in every clock cycle. So the one parameter for measuring the performance is throughput. If the pipeline functions in a smooth way like this, then in every clock we are getting one instruction out. Means the maximum throughput that can be achieved is CPI is equal to 1. Clock per instruction is equal to 1. CPI equal 1 implies one instruction processed in one clock. In other words, we can say throughput is the maximum number of instructions processed in a particular period of time or within a span of time. Here, one instruction processed in one clock cycle implies one instruction processed in 13 nanoseconds. In our example, the clock period is 13 nanoseconds. Hence, one instruction is processed in every 13 nanoseconds. This implies 10 power 9 by 13 instructions processed in 1 second. So the throughput is the maximum number of instructions processed per second. This is one parameter by which we can analyze the performance of pipelining. Another parameter is the speed up. We know that the execution speed of pipelined execution for n number of instructions is greater compared to the execution speed of non-pipelined approach. It means the time taken for non-pipelined execution is greater compared to the time taken for pipeline execution. Hence, with pipelining, we are having a speed up which is equal to the time taken for non-pipeline execution divided by the time taken for pipeline execution. So what is the time taken for non-pipeline execution? Suppose we have m number of phases and let the time taken for each phase be di. Then the total time taken for the execution of n number of instructions in this non-pipelined approach is the number of instructions into sum of all these delays. Number of instructions n into sum of the delays sigma I equals 1 to m di. Now if we are using pipeline approach for implementing this system, for each phase we are having a separate independent unit, hence there are m number of stages. We need to introduce interstage buffers and we need to set the clock period which is equal to the longest delay among these. That longest delay will be the sum of the buffer delay plus the longest among these delays. Now what is the execution time for this pipeline execution? We know that in pipeline execution, to fill the pipe it takes some time, and from then on for every instruction it will take one clock cycle. Hence, to get the first instruction out, the time taken is the number of phases into the clock period time, and then on for every instruction the time taken is one clock cycle. For the first instruction, the time taken is number of phases into clock cycle period. From then on, for the remaining n-1 instruction, the time taken is 1 clock period. Hence, for pipelined execution, the time taken is, for the first instruction, the time taken is number of phases into clock period, and for the remaining n-1 instruction, the time taken is 1 clock period, where the clock period is set to the longest delay. And the pipelining gives the best performance if each phase is having same delay. So first we shall consider the ideal case pipeline performance in which every phase is having the same delay. So the delay within each phase is equal to d. Now what is the clock period? The longest among all these d delays is d plus buffer delay. Since this buffer delay is very small compared to the processing delay, we shall consider it as negligible for considering the ideal case pipeline performance. Hence, the clock period is equal to D. Now, what is the time taken for non-pipelined execution? N into M into D. And what is the time taken for pipelined execution? 1 into m into 1 clock period plus n minus 1 into 1 clock period. What the speed up then? N into m into d divided by m into 1 clock plus n minus 1 into 1 clock. In this ideal case, 1 clock period is equal to d, so we shall cancel this and become n into m divided by m plus n minus 1. Rearranging n into m divided by n plus m minus 1. Now we shall take n out. It becomes n into m divided by 1 plus m minus 1 by n. So we can see as n tends to infinity, the speed up approaches m, where m is the number of stages. So this is the maximum speed up that can be attained with pipelining, which is equal to the number of stages m. For that, the number of instructions should be very large. Not only that, here we consider the ideal case in which every phase is having same delay. But normally different phases will be having varying delays, hence this m into d value will be less than this ideal case value, and the clock cycle period is set to the longest delay plus buffer delay too, hence this denominator value will be greater than this ideal case value, means the speed up will be less than this. So the target of pipelining is always a maximum speed up of m, where m is the number of stages, and a maximum throughput of CPI is equal to 1. But because of the time taken to fill the pipeline, the time taken to drain the pipeline, the use of interstage buffers, the difference in the delays, and setting the clock period which is equal to the longest delay, and also due to some additional issues called hazards which we will discuss later. Because of all this, the pipeline system is not 100% efficient to give a maximum speedup of m or a maximum throughput of CPI equals 1. So we can say the speedup is equal to efficiency into m. If the pipeline system is 100% efficient, then the speedup is equal to m. But usually in practical scenario, the pipeline system will not be 100% efficient. Hence, the speedup value will be usually less than m.